for the afternoon session. We have two workshops actually this afternoon by Dr. Federico Renda and by Dr. Hadi Sadati. And before introducing the first speaker, just let me remind some housekeeping rules. So I remind you to keep your camera and mic off during the presentation, at least for the theoretical part. Then if you have any questions, you can write them in the chat tool, or in any case, we will have some time at the end of the sessions for some question and answers. So, okay, so let's introduce the first speaker. Actually, it's a pleasure to me to introduce Dr. Federico Renda. And about his background, Federico Renda is an assistant professor in the Department of Mechanical Engineering at Khalifa University in Abu Dhabi. Before joining Khalifa University, he was a postdoctoral fellow at the Biorobotics Institute of Scuola Superiore Sant'Anna, where he also received his PhD degree in 2014. Then Federico Renda joined the lab at MIT Atlantic and the Defrost lab in Riyadh as a visiting professor in 2018 and 2019, respectively. He currently serves as associate editor in several prestigious journals, such as Soft Robotics and IEEE Robotics and Automation Letters. And his research interests include dynamic modeling and control of soft and underwater robots using principles and geometric mechanics. And today, his workshop is about SoRoSim, a MATLAB toolbox for soft robots modeling. So, Federico.
Hello, everyone. Good afternoon, good morning, good evening. Thank you, Matteo, for the introduction. I'm very happy to be introduced by Matteo, very good friend of mine, colleague. Actually, he was there at the beginning of this journey. Okay, I think you can see my screen, right?
Yes, we can. Yeah, in full screen mode now.
Perfect. Okay, so let's start this description of the SoRoSim MATLAB toolbox. With me today, there are Anup, Matthew, and E-Class Ben Mida from Khalifa University that are the developer of the toolbox and will guide you in the hands-on experience after this first theoretical part. Okay, so in a nutshell, what is this geometric variable strain approach that we have implemented in the toolbox? So, all of us is familiar with the standard rigid body modeling of traditional rigid robots. We used to parameterize it using the joint coordinate, and this produces a minimal set of ordinary differential equation in the standard Lagrangian form that we all like and enjoy. This model also enjoys co-location of sensors, actuator, and degrees of freedom. And for all of these reasons, it's very suitable for design, analysis, and control other than simulation. So not only simulation, but also all of that. The geometric variable strain approach aims to generalize this approach to the case of soft rigid hybrid system. So the main idea to do that is to see a soft link as a distributed joint and to parameterize this distributed joint with a finite set of strain modes. Once doing that, and after applying many principles of mechanics, we can obtain a model that indeed inherits all of these nice properties from the rigid body case. Okay, so an outline of this presentation. We will start with very few geometric mechanics background. For those of you who are completely unaware of it, this will be far from exhaustive, but I think it gives you at least few references that you can use to navigate the rest of the presentation. Then I will give you some more detail on the theoretical framework of the geometrical of our method. Then I will continue with some computational approach. If I have time in detail or less, depend. I would like to save time for the hands-on experience, which I think is the most useful one. And finally, I will briefly show you some numerical tests and example from the toolbox that you're going to learn in this tutorial. Yeah. Okay, so these kind of models are based on geometric mechanics, or even better, a part of geometric mechanics, the one that deal with the Lie group of rigid body transformation. Those are some reference that I have used to learn those things, and I'm still using to learn those things. And I really encourage you to have a look at those great books in this slide. Okay, so what is the rigid body transformation? I hope many of us know. The configuration of a rigid body in space is an element of what is called a special Euclidean group, which can be represented by a homogeneous matrix of this form, where R is a rotation matrix and small r is a position vector. Now, there are at least two ways to define this rigid body transformation G. In this presentation and in all the robotics literature, I would say, G map vectors, homogeneous vector in the local body frame B, this one, to the spatial frame, this one. Okay, one could define this in the opposite way, like for instance in the aerospace communities often done. Now, if we have an interconnected system of rigid body, then we can define the configuration space as a subset of the free configuration space. So the free configuration space is the Cartesian product of Euclidean group, special Euclidean group for each of the body. Then the interconnection limit this space, so those bodies are not free to move everywhere. So the configuration space is not the full set of special Euclidean group, but is a subset specified by the kind of constraint introduced by the joint. Now, this configuration space needs to be equipped with coordinate in order to compute anything, right? In robotics, as I introduced before, we use the joint coordinate, which is also a minimal set representation. Another possible choice would be to use, for instance, the position and the orientation of each of the frame, but this will lead with a maximal representation that also require additional constraint, right? So we have these two extreme: minimal representation where all the constraints are already involved, or maximal representation where no constraints are involved and you need to add them into the equation explicitly. Okay, let's move now to the differential of rigid body transformation. So if we apply elementary rigid body kinematics, we can lead to this formula, which relate the velocity of a point of your rigid body, P, expressed in the spatial frame. How we can compute it? We know, I think, that this can be computed by taking the velocity of one point of your rigid body, for instance, the origin of the body frame attached to the rigid body, plus another vector which is due to the angular velocity W of your rigid body. Now let's take W and RB, which is the vector of P in the local frame. Let's take these two in the local frame. Then in order to have the velocity in the global frame, we multiply by the rotation matrix. So all of this is in the global frame or spatial frame. Okay, how we can use this expression coming back to our matrix notation, homogeneous matrix notation. This very expression can be expressed with this product of matrix, this three matrix product. where the first one is your original rigid body transformation that define the position and orientation of your body. These other metrics here that we call velocity twist, where this tilde, it's such that omega tilde r is equal to omega cross r. And this is the velocity of your origin into the local frame, so pre-multiply by r transpose. So giving a name to all of these metrics, we have G multiplied by eta, where hat takes the 3 by 3, the vector omega and the velocity and construct this 4 by 4 matrix, multiplied by your original position RB. But if you recall, we have also before wrote down this equation here. Now let's take the time derivative both sides. We have RP dot 0. So there should be indeed 0 here, I guess. RP dot 0 is equal to G dot, and the 0 here as well. Sorry for that. No, sorry, this is 1, pardon. Okay, RB1. Now we don't have the derivative of RB because RB is fixed. It is a rigid body, so the point P is fixed in the local frame. So what we have discovered basically here is G dot. G dot as G multiplied by eta, where eta is this 4 by 4 matrix here that we call velocity twist. This velocity twist is an element of the Lie algebra of the special Euclidean group. Now, we can define this also in the spatial frame. Imagine that we define this velocity vector here, like G eta G minus 1. What happens if we place this definition here? We obtain exactly G eta. So it means that G dot is also equal to eta S G, where eta S is defined as such. If you do this computation, you will notice that in the 6 by 1 representation of your twist, you can compute this multiplication here using 6 by 6 and 6 by 1 matrix in this way, where we have used the adjoint map and the velocity twist in the body frame. Okay, so as you can see, the velocity twist in the body frame is the 6 by 1 representation of this 4 by 4 matrix, pre-multiply by the adjoint, produce the twist in the spatial frame. Now, what is this twist in the spatial frame? This is a big idea for the use of screw theory or Lie group in mechanics. So we imagine now our body to be extended everywhere in the space. And the eta S is the velocity of the origin of the spatial frame as a point of this extended rigid body. And you can recognize, I hope, this in this formulation. You have that the angular velocity part is just equal to the same angular velocity but rotated in the right frame, while the linear velocity is obtained exactly using an expression like that. You start from the velocity of this point and you add the angular velocity, sorry, you add the velocity due to the angular motion. Okay, so this is very important to realize. So in this theory, every point is a point of the body, if you want, and the body is extended everywhere. Okay, let's move now to force and wrench. The force wrenches are element of the dual of the Lie algebra, and they're made by the moment and force resultant. So the sum of the force and moment apply to, again, the origin, to the frame of interest, in this case, again, of the extended rigid body, as before. So we define, for instance, F in the local frame as m and n. So these are just the moment resultant and force resultant as you know them from standard dynamics. Now, how we see how this range transform from one frame to another? There are many ways. One of them is to use the power. So here we are taking the dot product between your range and the twist in the same frame, f and eta. So this has to be invariant with respect to coordinate and with respect to frame. So which means that the same range dot product to the twist in, for instance, the spatial frame needs to be the same. Now you replace the spatial twist with the transformation of the body twist, and then equating these two, ft equal to fst adjoint g, you obtain this relation that tells you how to transform ranges from one frame to another. The explicit formula for the adjoint minus t is this, and we also indicate this with adjoint g star. Now, what is the result? The result is, not surprisingly, the resultant of moment and force in this other frame. You should recognize it. The force are just rotated, and the moment are the one that were before plus the additional moment due to the moment done by the force here. So if you move the resultant from one point to the other, this is what you obtain. Okay, this concludes this very brief introduction to some of the concepts required to understand a little bit the model. Now we will start with more detail on the geometric variable strain approach. Again, here you can see some references that are useful if you are interested more in what we are presenting. Okay, let's consider now a floating hybrid soft rigid system composed by rigid and soft link. So once again, the configuration of each of this body with respect to the predecessor is defined as a curve this time in the special Euclidean group. The curve is parameterized by a curvilinear abscissa x that goes from 0 to L, where L is the length of your soft link. So x point to the cross section of your soft link. For each of the cross section, a element of the special Euclidean group define the configuration with respect to the predecessor, in this case with respect to the base, or for this link, for instance, with respect to the previous link. That's why there is this I here. Now, it's very important here to note that this continuous definition, G as a function of X, is clearly convenient for soft robot, for soft link, but also for rigid link. What's the meaning in that case? We take X as going from 0 to 1, where 0 point to the reference configuration of the rigid link with respect to the previous link, and 1 point to the actual configuration, where by actual I mean after the action of the joint itself. So we can, and of course, clearly all of these intermediate cross-section, if you want, they are virtual. They don't exist really, and they don't participate in the energy of the system. But it is useful to imagine them in order to make this analogy between a soft link and a rigid link. Okay, now we can take the partial time derivative of the configuration G. I indicate the time derivative with dot, and as we see before, G dot produce the velocity twist with the angular velocity and linear velocity here. This is relative to the previous body. Now, thanks to this continuous definition, we can take the partial derivative with respect to space, with respect to x, and we indicate this with prime. This produces a strain twist that that is exactly similar to the velocity twist with an angular strain and a linear strain here. Now, we can notice that this expression is a matrix ordinary differential equation that can be integrated in space. Integrating this in space produce an exponential, in particular the exponential map in SC3, which has a very nice analytical formulation here. Now, for the case of rigid link, the strain is nothing else than the joint screw itself. It's nothing else than the axis of the joint and the strength of your joint motion. So which means that the strain twist for a rigid link is always constant, if you want, with X. So C for the case of rigid is always constant. While for the general soft case, the strain is not constant with X. Clearly, this can change from point to point. So in order to make this integration, we need to use what is called the Magnus expansion, which we will see later. For now, just think of it as a function of your variable strain. Okay, so we have introduced our exponential coordinate that are directly the joint screw for the rigid case and this Magnus expansion, or again, a function of the strain for the soft link. Let's move now to the differential kinematics. So we seek now to find a relation between the time derivative of the strain, that are our coordinates, and the link velocity and acceleration. How to do that? So we start by equating the mixed partial derivative of G. And if you do that, you immediately find this relation that are called transpositional relation. Those are very, very important because they relate velocity, relative velocity and relative acceleration, their derivative with respect to space, with the derivative with respect to time of the strains, plus other terms that involve the use of other SC3 operator reported here for completeness. You can imagine this operator more or less as the derivative of the big add that we introduced before. Now, once again, this transpositional relation can be integrated in space. They are matrix differential equations that can be integrated, at least formally, and this is the result of your integration. Now, and this is a fundamental relation because it relates what we were looking for, the relative velocity and the relative acceleration, with the time derivative and second time derivative of the strain. Now, this general formulation is valid for soft link, but also, and this is quite nice to note, multidimensional rigid links, such as spherical joint. As we observed before, in the case of rigid joint, the strain are constant, so we could pull them out here of the integral. And also there are other consequences if the strain is constant that we will see later on. Let's now recover the traditional robotic case when your strain is not only constant, but also one-dimensional. This is really the most common case in robotics. Now, in this case, all of this additional term goes to zero, so your transposition relation is said to be exact. And then the integration becomes trivial, and we recover the simple relation between the joint screw, the derivative of the joint screw, and the relative velocity of your link. Similarly for the acceleration. So this is, I hope many of you are familiar with this relation. I think it's interesting to see that indeed this is a consequence of the general formulation we are presenting here that also include different kind of situations such as soft link and multidimensional joint. Okay, another important piece of the model is the discretization of the continuous field. So far we left our strain to be variable, but in order to make some computation, we need to discretize this infinite dimensional field. So how we do that? By employing a finite set of strain mode represented by a matrix B. Doing so, our strain can be written in this form, where Q is our new generalized coordinate for the soft link. And Xi star represent the strain of the link in the unloaded configuration without any elastic energy inside. Okay, what we can do now, let's take back the differential kinematics we developed before, and let's plug in our discretization for the soft link case. Let's then take Xi dot. What is Xi dot? Xi dot become B Xi, which is a function of x. Also, Xi dot is a function of x. Q dot. This is constant in time, so disappear. And notice that only B depends on x, not Q. Q depends on time only. So when we plug these things inside here or in the other, in the same relation for the relative acceleration, we can pull out our generalized coordinate. Now, those are relative velocity and relative acceleration. To obtain the absolute velocity, you need to add the relative velocity all along the chain. And this is what we are doing here. And these two operations define the geometric Jacobian for a soft link. Again, it's interesting to note that the standard geometric Jacobian of a rigid chain is also represented by a special version of this equation. Okay, similarly for the acceleration, which define also the time derivative of the Jacobian. All right, this was a very important result. Now we have the Jacobian and its time derivative. Now we want to develop a dynamic model. How to do it? So we start with the free dynamic of a rigid and a soft link. So let's take a rigid link that floats in space without any connection. So it's free to go everywhere. So the dynamic of this single body system is represented by the well-known Newton-Euler equation, which is here, is exactly what you know already, but just by using this SC3 or Lie group notation. So on the left, we have the conventional inertia force or effective force. And on the right, we have the force acting on the system that are external forces, and also the force due to the joint attached to it of the adjacent body. For our soft link, we can use the Cosserat rod, the PDE of the Cosserat rod dynamic, partial differential equation. Again, in the Cosserat rod dynamics, we also use rigid cross-section. So this dynamic perfectly align with the kinematic assumption we have made so far. Those are the PDE that I would like to show you that they're not so different than the Newton-Euler equation. On the left, we have the same effective inertia force. Now we only use distributed inertia instead of lumped inertia, but the equation is the same. On the right, also you have the sum of the force, distributed force, and the derivative of the internal forces. Just because it's a PDE with 1 over meter dimension. And here you have the boundary condition that again are due to the joint force attached on the two ends of the link. Now, how we can model the internal forces? So there are generally two kinds of internal forces: elasticity forces, and here, for instance, is represented a linear hook-like relation. However, in fact, any constitutive law can be applied here. for instance, such as the one that Matteo presented you, I think, yesterday. Okay, while another important things, the internal, the internal actuators, such as cable that run inside of the soft link, can also be modeled very easily as internal forces with their own constitutive law, if you want. This is where U is the strength of your actuator. Imagine a cable, this is minus the tension of the cable, and this just distribute this force to obtain the moment resultant and force resultant on your cross section. So this is all you need to, in order to do that, is the distance of the actuator to the midline, nothing else. Okay, now that we have a free dynamics and we have a Jacobian that parameterize the allowed motion of the system, we can use the Lambert principle to project the free dynamics onto the allowed dynamics. So those bodies, they're not free to move any way they like. They are constrained by our joint and by our, for instance, constraint that we can make on the soft link. It can be only rotational link, can be only springs, for instance, whatever. So we use the Lambert principle, and we sum over all the cross section and overall the body. By doing so, you obtain the standard Lagrangian dynamics model in the standard Lagrangian form. This could also be obtained from Lagrange equation if you want. It's just a little bit more complicated in my opinion, instead of using the D'Alembert principle, but this is exactly the Lagrange equation that you know. With the mass matrix, Coriolis matrix, stiffness matrix, actuation matrix, and external generalized force vector. So let me check the time. Okay, I will try to go a bit faster now to show you how to compute now all of this quantity. We have to compute, for instance, the Magnus expansion. We have to compute the Jacobian, which is an integral of something. We have to compute the mass matrix, which is another integral, and so on. How to do that? There are many ways to do so. We present you one of the possibility, that is the one that is also implemented in the SoRoSim toolbox. So let's start with the constant strain case. Why we do that? First of all, because this is exactly the case we have for rigid body. As we, in our formulation, rigid body has always constant strain, and this strain is equal to the joint screw. And also it introduced some quantities that are useful later on also for the general variable strain case. So with this assumption, the Magnus expansion is super simple. It's just the product of the constant strain and the curvilinear abscissa. And this is also what we have already used for a rigid link. We already use this Magnus expansion here. Now, this assumption on the differential kinematics has two consequences. One of them, as I already said, is that the strain is constant, so you can pull out of the integral. The second consequence is that it appeared this integral here, which is called tangent operator of the exponential map. Is another nice operator of SE3, which has been computed by people much smarter than me, and you can find in books. Similarly, for the relative acceleration, again, it make appear just the derivative of the tangent operator of the exponential map, which also have a nice analytic formulation. So in conclusion, in the constant strain case, everything is analytic. The configuration is analytic. The Jacobian can be computed analytic. The time derivative can be computed analytic. And consequently, all the Lagrangian metrics can be computed analytically. This should not be a surprise because this is the case of rigid robots. In principle, rigid robots dynamics can be computed completely analytically. Now, let's move to the general variable strain case. So now we don't have any more full analytic expression. We want to compute those Lagrangian matrices that are integral of stuff. So the natural choice is to use a Gaussian quadrature scheme. So we seek to find the integrand of those matrices in several points inside the domain of integration. For instance, in this picture, we use 3 quadrature points. You can use, of course, 5, 10, or more. Depends on the order of accuracy you want to get in the computation of those matrices. So what we need to get is the configuration Jacobian and its time derivative at those quadrature points. How we do that? Let's start with the configuration. So what we do, we take an approximation of the Magnus expansion. So the Magnus expansion is an infinite series. So if you want to compute it, you need to truncate and approximate somehow. Again, we use the Zanna collocation approach in order to approximate the Magnus expansion a different order. For instance, here a 4th order is reported, but there are 6th order or whatever order you want. For a 4th order, for instance, you need 2 values of your strain in between an interval, between 2 consecutive Gaussian quadrature points. So once the Magnus expansion is approximated, then you can use the exponential in SE3 to compute your configuration. You can jump all over your chain to find the configuration of all the points that you want. Let's see what we can do for the Jacobian and its time derivative. So what we observe is that gamma over h, where gamma is the approximation of the Magnus expansion and h is the length of an interval between 2 Gaussian quadrature points, though this quantity behave as a constant strain approximation, if you want. So we can apply the analytic formula we found before. To do that, we need to take also the time derivative of this approximation of the Magnus expansion. And then we can apply the analytic formula we have used for the constant strain case, at least to find the relative velocity and the relative acceleration, where now by relative, I mean relative to the previous Gaussian point. All right. Now that we have that, again, you can sum relative velocity and relative acceleration all along your chain to obtain a recursive formula for the Jacobian and its time derivative. Okay, so in conclusion, what we have used is a 2-level nested quadrature scheme. You have one quadrature scheme to for the Zanna collocation method on each of the interval, and then you have a global quadrature scheme for your Lagrangian matrix. Very quickly, some numerical tests. Here is a very long 100-meter long cantilever beam with a tip follower force. Here we use only 5 degrees of freedom, and we have, in fact, recovered exactly geometrically exact finite element method result, but with much, much less degrees of freedom. Imagine to do that with a finite element method, you need a lot of nodes, not only 5 degrees of freedom. Then we test the conservation of energy of the numerical scheme. Here you can see a 4 degrees of freedom cantilever beam subject to gravity and undamped. There is no damping whatsoever in this system. And indeed, in our numerical scheme, we see that the energy is conserved. Although kinetic, gravitational, and elastic energy exchange a lot during the simulation. some other example, cable-driven manipulator, subject to gravity with any kind of custom, any kind of path for your actuators. We can have, of course, hybrid soft-rigid chain, and we can actuate the system imposing the motion of the revolve joint that is attached to the first link. And also here we model an underwater soft vehicle with interaction with water as well. And here also we impose the motion of the motor that rotate, and everything else is passive and computed by the toolbox. Okay, I think I take enough time from this part. If there are some questions on this part, is welcome. It's normal if you don't get all the point. I would suggest to go to the practice session with the Anup and E-class. Thank you very much for your attention.
Thank you very much, Federico. So if there is any other question, of course, you can also use the chat tool, the chat box in the Zoom software. And so let's proceed to the hands-on part. Yeah, maybe actually there is a question. I don't know, Federico, if you can just...
I don't see anything in my chat. Also, maybe
okay, no. Actually, there is a hand that has been risen. That's why.
Okay, I don't see anything like that. Maybe because I have an old version of Zoom.
Okay, don't worry. I'm here for this.
Thank you very much. Please.
Camillo.
So, hello. Thank you for the presentation. It was very interesting. I've got just a curiosity on the last slide you showed us when you use cable actuation for the flexible joint, and I saw that you somehow wrapped the tendon, the cable, the actuating cable around the joint, and this leads to multiple degrees of freedom for the joint. How can you obtain that? It's just a curiosity. How can you obtain that deformation modes with a single cable?
Okay, I think maybe I can quickly share again the slide. So this is what you're referring to, right, Camillo?
Yes. Yes,
so in this example, we have only one cable, you're right, and the path of the cable is quite strange. Initially is straight, and then it has a helical shape. It's not around, by the way, it's still inside, but it has an helical shape. So the question is how not to obtain a different deformation with a cable with this path. The point is that so first of all, you obtain different resultant moment and force resultant for each cross section, which already by itself could provide a complex shape. Furthermore, even if you have a straight cable, but the elasticity of the cross section change along the arm, the equilibrium between those two internal forces, elasticity and the cable, have a different result for each cross section. So it's really easy to obtain crazy shape.
Okay. So the point here is that the more you pull the cable, the more section you are actuating.
No, they're always all actuated, because the cable, I mean, the tension of the cable is transmitted instantaneously. So the full cable is under tension.
But I see that during the time, it gets a different deformation.
Yes, because the tension of the cable goes from 0 to a certain value linearly. So at the beginning of the at the beginning of the simulation, the tension is 0, and at the end is a few hundreds. So there is this, exactly.
So you just start actuating the tip, and then when
not the tip. Sorry, not Camilo, not the tip. It's everything together. It's not the tip. It's not a tip. It's just from 0 to something. But with a cable, you cannot actuate only one part, because the cable is in tension all along your soft link. You can, in principle, if you could control the tension of the cable locally, then yes, you can only tend the tip of the cable. But with a normal cable, you can only pull the full cable together, right?
Okay. Thank you
and
so
maybe,
much.
yeah, maybe it can help also to remind that in this device, the cable is running through the entire structure, but is fixed at the tip. If I'm not wrong, Federico,
yes.
it's pulled by the base from the base. So there is only one point where there is this pulling force.
Yes.
Probably the video is the result of these nonlinearities that are developing in time when the increase of pulling force is exerted.
Great.
Okay.
I will, if I can suggest to move to the
yes, please. Of course, if there are other questions, you can type the question in the question box in the chat, and Federico, I'm sure you will be happy to answer directly or maybe by email afterwards. I don't know if we have some time, but maybe we could move on the hands-on part.
So Anup and Niklas, my collaborator, if you like to share your screen.
Hi everyone. So me and my colleague Niklas will be doing the hands-on section for the toolbox. First of all, maybe we can start by sharing the toolbox we developed in the chat. So is it okay if we share it in the chat?
Yes, I think so.
So, right now I'm uploading the zipped version of the toolbox in the chat. So everybody in the chat will be able to get the toolbox and use for themselves. They can also download the same from a link that class will be sharing soon. So I will start with introducing the toolbox and so on. I will share my screen. So once you install the toolbox, you can go to the toolbox folder. Then we start creating the links and linkages of the system. So by links, we mean either a rigid body or a soft body, which are part of the robot or the linkage. So the way we define a link is just by saying a link name with an equal to sign and saying link. Then a dialog box will come that asks the user to say whether you want to create a rigid link or a soft link. So before we go into any problem, let us try to imagine a simple problem of a double pendulum, a rigid body double pendulum. So a double pendulum will have two rigid links and with the revolute joints. So that is our imagination. So based on this imagination, we are trying to create the first link of this double pendulum. So because it's a rigid link, we choose rigid. Then another dialog box will appear, which will ask you certain properties of the links. So the first property that the dialog box asks is the type of the joint. And for this particular case, because we want a revolute joint, we will choose R. But there are several other options such as prismatic joint, helical joint, and so on. The second question is density. For now, we will just keep the same density. You can also change these properties later. I will show it in a minute. Going on, third one is the cross-sectional shape. So at the moment, we can have two types of cross sections. One is circular, another one is rectangular. We'll stick to the circular cross section. Then the third and fourth properties are the coordinate, y coordinate of origin and z coordinate of origin with respect to the previous frame. For now, we'll just keep the same. Maybe going on for the other examples, we will try to explain how we change these properties. And Here it is asked to input the length of the link. Let's say we want to have a half-meter length. So we'll just enter 0.5. The units are in meter, so just enter 0.5. Then, because we choose circular cross-section previously, it will ask initial radius and final radius of the link we are creating right now. Let me just give a radius of 2 centimeters, and initial and final radius, I'll just keep it as 2 centimeters. And once you press OK, a link will be created with the name L1 with the following properties. So it will show the properties of the link. Firstly, the link type. Because it's a rigid link, it will show R. If it is a soft link, it will show S. The cross section, abbreviated by CS. NP is the number of P's. So this is one important thing which should be noted. So for a rigid link, the number of P's will be always 1. And for a soft link, the number of pieces will be the joint plus the number of divisions of the soft link. So later I will show an example of a soft link with 2 pieces, 2 divisions. So in that case, number of pieces will be the joint number for joint and 1 number for each division. So it will be 3 pieces for a 2 division soft link. Going on, third one will be the joint type. Because we choose Revolute, it is R here. This XS, WS, and N GOS are properties of soft links, which will be explained in a later example. And we have the initial and final radius, RI and RF. Because it's a circular cross section, the properties such as height and width are not valid for this kind of a link. We have the L here. LP is a property for soft link, which will be explained later. CX is the length from the origin towards the center of mass of the link. So for this particular example, we know that a rigid link with the length L and uniform cross section, the center of mass will be half of its length. That is why we can see that center of mass is 0.25 and length is 0.5. Similarly, we have Y coordinate, Z coordinate, E, Young's modulus, Poisson's ratio, shear modulus. These are all properties of soft link. So that will be explained later. Rho is the density we just gave. Mass is the mass matrix, inertia matrix for the link. So all these properties can be accessed later and can be changed. And we have the color here, number of divisions, number of cross sections per length, and number of points per radius. So these are all plotting parameters. All these can be changed. Let us try to change the length of the link. Now currently the length is blue. These colors are similar to MATLAB colors. So anybody who is familiar with MATLAB would know that if you use B for color, it will be blue. Similarly, if you use red for R, it will be red color. So let's change the color to.
You forget. I think you forget to put point.
Yes. Okay. Yeah, we need to type L1 and to access any property, use a dot, then type color and each type. I need to create the link again.
Yes.
Now I just changed the color. To do that, what you need to do, L1 dot color equals, let's say, red color. So now you can change that the color is updated to red. At this point, you can try to change, let's say, the center of gravity. You want to keep it same as the length. What you need to just do is L1 dot CX equal to 0.5. Now, the center of mass of the link is exactly at the tip of the length. Similarly, you can access all other properties. For example, I just show you how you can access the mass, the inertia matrix of the link. So if you type L1.ms, it will show the inertia matrix of the link. What we see here is the moment of inertia with respect to X, Y, Z axes, and the mass of the link, which is 0.62 kilograms. these three, the last three diagonal elements are all masses. So any of this can be changed for the problem. Let us create another linkage because we are planning to make a double pendulum simulation. So we need to have another link. Let us create a link to L2 as second link. Then again, it's a rigid link. Let's choose rigid, and it has revolute joint. So we'll choose R. And for this example, let's try to keep a rectangular cross section. So we just choose a rectangular cross section here, and the length, let's keep it the same as the previous length, which is 0.5. Press OK. Now it will ask, instead of initial radius and final radius, now it will ask initial height and final height, and initial width and final width. So initial height, we will keep the same. Final height and final width, let us keep the half of the original height and width. So after that, you press OK. Now you can see that the second link is created. To create a linkage, what you need to do is you can combine these two links in any order. So what you need to do is type a linkage name, which is the name of the robot which you want to create. For example, this is a double pendulum. So we can even type double pendulum equal to linkage L1, L2. Once you do that, an image and a dialog box will appear asking the properties of the linkage. So for this particular example, the first link, because I created a second version of the link, it's appearing as a fixed joint. Let us fix it by just changing the. So L1 is a fixed joint because I created it a second time. So we can just change it by typing joint type equal to double. Then let's create the double pendulum again. It will ask the axis of rotation of the first link. Let us, in this image, the arrows are colored according to the axis. So the x-axis arrow will be always colored red, y-axis will be green, and z-axis will be blue color. So because we want rotation about z-axis, I will choose z. Then it will ask for the second link, the axis of rotation. It will be, we will again choose z. Then after that, we need to enter the reference configuration. So reference configuration means how you want the linkage to appear in its reference state. For example, if you want to keep an angle for the second link, we just need to type, let's say we want 45 degrees for the second link, just type 0 pi by 4. Then the link will be automatically adjust in a way that the second angle is pi by 4. So let us, if you don't want to save this configuration, we can redo this process again. Let us redo this process so that the initial angle is 0. Confirm. I will not confirm. No. Then these questions will be again asked. The axis of rotation for the first and second revolute joints, and the reference configuration I will keep as 0. After that, you confirm the geometry. Then the question will be asked to enter whether the system is subjected to gravity. You'll choose yes. And the direction of gravity is asked. So again, for all these directions, we can look at the arrows indicated in the image to choose whether the direction is consistent with the problem. So let's say we choose a direction of -y and press OK. The next question will be whether the system is subjected to an external point, force, or moment. So there is one thing to be noted here. For a rigid link, the point force or moment will be acted at the center of mass of the rigid link. For a revolute joint, for a soft link, the same will be acted at the tip of the soft link. So this is something you need to be aware of, because we put similar problems like that in the assignment questions we developed so that you can later use it. So that's about that, the point force or moment. So for this particular case, I will just use no. Then the last question will be to answer whether the system is actuated or not. So it has two revolute joints. We can actuate these two revolute joints to give a torque commanded actuation or a angle commanded actuation. So because we want to just simulate a double pendulum without any actuation, we just keep not actuated. Now another question will be there to ask whether the joint has any stiffness or not. If you keep a value for the stiffness for the joint will act like a torsional spring rather than a revolute joint. So for this example, we'll just keep 0. For the second joint as well, we'll just keep 0 as the value for torsional stiffness. After that, the joint, the linkage or the robot or the double pendulum is created. So once the double pendulum is created, we can try to run some static or dynamic simulations. Let's try to run a static simulation. For the double pendulum, to run the static simulation, what you need to do is type the linkage name, then a dot to access its properties or methods. Then for the static simulation, just we need to write statics. Then it will ask for the initial condition. So let's try to give a -1 radians as the first initial condition and -1 for the second one. It will run a static simulation showing that it is vertically downwards. Similarly, we can do dynamic simulations by just by typing dynamics. Again, you'll ask for initial condition of joint coordinates as well as their velocities. Let us keep it at the horizontal position and we'll see what happens with the gravity, how it moves. Simulation time can be adjusted here. Then by pressing OK, it will run a simulation for 5 seconds and it will plot the result of the simulation if you press S. So what we see here is the simulation for the double pendulum which we just developed. So it is plotting all the points and this plotting will continue till time reaches 5 seconds. For the sake of the example, I just stop this simulation and explain some more properties of the linkage as well as the plotting. So now double pendulum is our linkage now. It has several properties and methods that can be used. All these methods and properties are mentioned in a startup file provided with the toolbox. Detailed descriptions of linkage properties are all mentioned in this file. We also mention the methods that are available for this particular linkage. For example, if you want to find the generalized mass matrix associated with this double pendulum, we need to provide what we need to do is just type double pendulum dot generalized mass matrix. Then the input should be the joint coordinate for both the links. For this case, there are 2 degrees of freedom. We'll just let's find out the generalized mass matrix for the configuration Q1 equal to 0 and Q2 equal to 0. So you'll get a 2 by 2 matrix. So this indicates the generalized mass matrix when the configuration is 0 and 0. The result of static and dynamic solution will be saved in the folder where which the simulation is run. So for example, if we double click on the dynamic solution to the MATLAB workspace, the time and velocity joint coordinates and their derivatives are loaded to the workspace. Let's say we access QQD. We have QQD and time in the workspace at the moment. If we want to access, let's say, the joint coordinates and velocities at time t equal to 1, what we need to do is type a variable name in rep1. So this is for t equal to 1 second if you want to access velocities, joint coordinates and velocities at t equal to 1 second. The answer will be, the first 2 elements will be the joint coordinates. The last 2 variables will be their velocities. So if we just want the joint coordinates, we can access them by doing this. And if you want their velocities, we can do it by saying this. Now, if we want to compute the mass matrix at time t equal to 1, what you need to do is just input the joint coordinate we found for the generalized mass matrix. Now, generalized mass matrix will be calculated at time t equal to 1. Similarly, we can do generalized Coriolis matrix. And how we access the file will be described in the methods. So we need both joint coordinates and their velocities to calculate the generalized Coriolis matrix. To do that, we just input Q1 and QD1. So what we get is the generalized Coriolis matrix at time t equal to 1. So these properties and methods can be used to compute some calculations based on the simulations we just did. For example, if you have a generalized mass matrix and if you have access to the let's say the screw velocity at time t equal to 1, we can find the kinetic energy of the system. If we have the forward kinematics of the system, we can find the potential energy of the system. So let me give one more example of how we can get the forward kinematics of the system at time t equal to 1. To do that, again, similar process. What we need to do is, instead of generalized Coriolis matrix, we just need to write double pendulum dot forward kinematics at t equal to 1, because Q1 is the joint coordinate at t equal to 1. The result will be a matrix where the transformation matrices of significant points are arranged one below each other. Significant point is another concept that is used in the programming of the linkage. So the description of significant points you can read from the startup file. I will briefly explain here. So for a rigid link, there are 2 significant points, one at the joint, one at the center of mass. For a soft link, there is significant point at the joint, and there is significant points at each Gaussian points, and at the start and end of the soft link. So there are several significant points for the soft link and 2 significant points for the rigid link. For the current example, as there are only 2 rigid link, you can find out that the last 4 rows will be the transformation matrix of the second link, which is second rigid link. And the y coordinate of the the second link at time t equal to 1 can be obtained as this number. So this number can be used to find the potential energy of the system, for example. Okay, so I will just quickly run the simulation for 1 second. Let us just run it for a second and finally plot. Now the plotting will be done for 1 second. Time is varied from 0 to 1, and we use a frame rate of 100 frames per second. You can change all these properties using the linkage class. For the linkage class, there is a property called plotting parameters. So this is a simulation. The simulation, once it is computed, it will be saved as a video in the current folder where you are running the simulation. So you can access the video file from the same folder. It will be saved as dynamic.avi. One more thing before I finish. So we have the plotting parameters of the double pendulum or the linkage you created can be accessed using double pendulum.plotting parameters. It has camera position. For example, for this planar problem, the camera view was the camera position was at this location. We can just make it along with the z-axis by just typing.
Yeah, and then if you can move to soft stuff, I think it's in the interest of time more useful.
Yeah, yes. Just let me just show this one time, then. So by changing the camera view, we can have any kind of view. So all these properties can be adjusted by just typing and indexing this by using the dot index. Now Iklas will explain you regarding the soft link.
Okay. Hi, everyone. Let me just share my screen. Okay. Okay, I think you can all see the screen.
Yeah.
Yeah, okay. So in order to define soft linkage, the first thing you need to do, as Anoop mentioned, is define a link. So you can start by defining a variable and equating it to the command link. And then the same procedure as the one we did for the rigid link, just choose soft. And you have like an interactive user interface where you can define all the parameters or geometric and material properties. So in this case, I'll show a simulation for a cantilever beam like rod. So using this, setting the joint to n means that it's a fixed joint, so it's fixed to the wall. And in this example, I'll use 2 divisions to demonstrate how you can set different degrees of freedom. I'll keep it as a circular cross-section, and I won't change the material properties, but you can change the density, Young's modulus, and other material properties as shown. After you set the material properties, you can define the geometric properties for each division. So in this case, we're looking at piece 1, which is the first piece of this soft link. Keep the length as 0.3. And then you can define Gaussian points. So you can set how many Gaussian points you'd like to use in this division. I'll leave it as 5. And for the radius, I'll set it to be 0.2. And then you have to do the same thing for the second piece. We'll keep the radius again the same. Okay. Okay, so now you've created a link that is a soft link. The Gaussian points we've set, we used 5, but 2 points are added to each division. 1 point at 0 and 1 point at the end of the length, while the rest of the 5 points go from 0 to the length of the division. And so you can see that you have 7 points for the first division and 7 for the second one. This XS are the X points that go, so the locations of the Gaussian points along the link, and the WS is the weight of each point, since following the same format as the Gaussian quadrature. You can see here the initial radius and the final radius of each link, of each division in the link. And because we use the circular one, there are no values for these properties. Okay, so I'll go on to creating a linkage. So I'll create a linkage called S1. So in order to do the static and dynamic analysis, you need to define a linkage, even if it's just consisting of one link. Okay, I'm starting to worry that you can't hear me.
No, we can hear you, yes.
Okay. So you define a linkage, and the same way we did in the previous example that Anup showed. So in the case of a soft linkage, you'll be shown the link that you've created, and you'll define the degrees of freedom for each division. So here we're defining the degrees of freedom for the first division. That's why we see it highlighted here. And these are the available degrees of freedom you can choose from. So in this case, in the case of a cantilever beam, we're expecting bending about one axis only. So we'll apply gravity in the negative y, and we expect a bending about the z-axis. You can also set the order for each degree of freedom. So the order is the order of the polynomial that is used to calculate the strain for each of these degrees of freedom. If you keep it as 0, this is considered as a constant strain case, which Federico explained earlier. Yeah, so you can, and it's important to note that your order should not be higher than the number of Gaussian points you decide to use. So just keep that in mind. Done for the first division. And then we move on to the second division, and you repeat the same procedure. So in this case, both of the divisions will react in the same way to the gravity. So I'm just setting the same degrees of freedom for both. So this is the same thing Anup explained, the reference configuration. So this just shows how your linkage will look before any forces are applied. So we'll keep it in the reference 0 strain configuration. And then if you're sure of the linkage you created, yes. And then you'll be asked if the system is subjected to gravity. In this case, yes, we want to see the effect of gravity. Define the direction of the gravity, negative y. And in this case, we won't apply any point forces or moments. Not actuated. Okay, so this is how the linkage looks. And this is the linkage after creating. So in the same way, we can test the static simulation for this by using S1, which is the linkage that we defined, and dot, and use the method statics. Once again, you'll be prompted for the initial guess. So this is like the initial condition of how the linkage looks. So this is how the soft link looks when gravity is applied in the negative y direction. In this case, we only observe the bending about the z-axis. So we can try a dynamic simulation in the same way, S1.dynamics. And then maybe we can start by keeping it at 0 and running the simulation for 3 seconds. Okay, so you have the option to plot the simulation or not. Let's see how it looks. So this is the linkage, and it's being released from rest with the gravity acting in the negative y direction. Again, you can change the view of the plot the same way Anup showed earlier by controlling camera position or the camera up vector. Okay. So this is how a free-falling cantilever beam fixed looks. I think after the dynamic simulation runs, if you have the image processing toolbox, you'll get a video that you can save and use for later analysis. So for the sake of time, I'll just move on to another simulation. So in this case, I'll show how an actuated soft beam would look. So once again, we can define a link. Soft. And again, we want to keep it fixed and just pull a cable and see how the link moves. One division. Okay. So the length, I'll set it to 0.75 using 9. And the radius, 0.03, okay, and this will keep it as half of the final radius would be half of the initial radius. And then, okay. So again, maybe we can look at changing. So you can change the properties of the link the same way that was shown earlier. So let's make a red soft beam. And then define a linkage. Okay. So in this case, you can see, for example, the n_L, which is the number of cross sections for plotting. In this case, we're planning to use a higher value of tension. So maybe like a finer or more cross sections would be needed. So let me stop this. So we can change that by changing the number of cross sections here. Right now it's 10. We can change it to 30, for example. And then recreate the cross section, the linkage. Okay. So you can see more cross sections are added for the plotting. You can change these based on how smooth you want your plot to look. Once again, in this case, we'll define the bending about all of the axes. And we'll give a higher Gaussian. Okay. So we want to apply gravity as well as the actuation. So we'll keep gravity in the negative y direction. And for now, we're not looking at any external point forces. And yes, we want to actuate the system. So first, you have to select how many cables or actuators you're going to use. In this case, we'll just use one. And then you're asked if the cable is fully inside the linkage or if it's, so in the case of an irregular cross-section, you can have the cable exposed in some points, but in this case, it could be fully inside the linkage. So yes. And then there are different types of cable paths you can choose. So you can either have no cable or a constant or an oblique, which is a cable at a slope, so a straight line with a slope. A helical cable would be one that goes helically along the linkage. But in this case, we can try a custom one. So for a custom cable, you can define equations that specify like the points of y along the x and z along the x. So I have previously prepared functions for these. So we can try and see how these look. Okay. And then you can set where your cable starts and ends. So for this case, we want it to be a full. We want the cable to go through the entire link. So we can go with okay. And then we can see how the cable looks. So this is how our cable goes from the beginning of the link to the end. And if you're not satisfied with how your cable looks, you can go again and select either custom or any other cable path and just redefine the points or the equations. So in this case, I'm satisfied with how this cable looks, so we can go ahead and press done. So now we have this plot that shows how the entire link looks. So we can run a static simulation to see at different values of the tension, how this cable would look, how the linkage will look. So S3 status. And then you have to define the value of the actuation force. So we want a pull, so it's a compressive force. So we can go with minus 50 newtons and see how the system behaves. We want to start from zero strain conditions. So this is how our soft link will look under gravitational forces and a 50 Newton pull. So we can try different values for the tension.
Just to add that a positive tension is like embedded McKibben actuator, for instance. If you have a pressure that extends your actuator, you can put a positive value here.
We can check how the positive one will look, but maybe depending on what degrees of freedom you have active, we might not see. Yeah, so there is no elongation active in this case, but if there was, we could see that the linkage would elongate based on the Young's modulus that you use for the material. So yeah, so you can test different values of the tension and you can use different equations to create the cable path.
This is the same cable path I show in the presentation, right?
It's slightly different.
Okay.
I changed some of the parameters here. But it's almost, it's just the amplitude that's different. I think Anup can show a few other simulations.
I think
the
we
under-actuated one.
Over time now. Maybe Hadi can grant us 5 more minutes, but no more, guys.
Yeah, please, yes, just few. Yeah, maybe a few minutes more and are fine, of course. We are not so strict, but yeah, try to conclude in the next 4 or 5 minutes, please.
Thank you. Thank you.
Okay, so maybe I can show you quickly one more example. So let us try to have a hybrid system with a rigid body with a revolute joint and a soft body with a spherical joint, for example. So let's create link 1. Rigid, just rigid, and we want revolute joint. I'm not changing anything else. I'm just changing the color of the link so that both links will have different colors, making it a black color. Now we have link 2, which is a soft link is a spherical joint. That's what I want. So I'll choose soft, and the joint will be spherical joint. And cross section, I'll just keep the same. I'll just increase the length to 75 centimeters. And radius, final radius, I'll just make it as 1. And number of Gaussian point, I would like to keep it as 9. So that is the second link. So now we combine these two links to make a linkage. Same procedure, linkage L1, L2. So now the question for the first link, the axis of rotation, just use Z. Then there will be a dialog box asking the degrees of freedom for the soft. So I'll just choose all rotational degrees of freedom with the linear order. Then press done. Now the reference configuration is set. We'll confirm the geometry. We'll add the gravity in the negative y-axis. Then after that, we will not add any point force at the moment. And then let's actuate the revolute joint in this case. So I'll actuate the revolute joint, yes. Then revolute joint actuate, yes. Then let's actuate the joint by angle. Now it's asking whether the spherical joint is actuated. We'll just choose a passive spherical joint. So we'll not actuate the spherical joint. Just no. Then you will ask whether the soft link is actuated. At the moment, we'll just say that soft link is not actuated. Torsional stiffness of the revolute joint will be asked. And after that, the linkage is created. So once we have the linkage, you can run the dynamics simulation by just saying dynamics. It will ask the angle of the revolute joint at function of time. I'll just use I times t. So it's like a frequency of half a hertz. Initial condition and simulation time will be asked. I'll just run a simulation for 1 second. So computation will be done. After that, you'll ask for a plot. Just press AS. Then what you will see is a simulation of revolute joint actuated at half a hertz frequency or half revolutions per minute. Then you can see the combined actuation load and the gravity force acting on the system, forcing it to have this kind of a dynamics. Yeah, so you can have different values for actuation, like you can give different kinds of inputs as a function of time. You can use even step function, like Heaviside function can be used. So all these possibilities are there for this toolbox. Yeah, so with this, I think we wrap the examples.
Thank you very much, Niklas and Danup, for the great presentation. Thank you all. And now, Matteo, we leave back the floor to you and to Hadi.
Yes, great. So let me thank Federico and his collaborators once more for this in-depth introduction